So our next speaker is Sumanto Chakraborty. Sumanto, so you will have around 50 minutes, so that 10 minutes can be devoted to questions. I shall give you a 5-minute warning.
Thanks to the organizers, of course, for inviting me to give a talk here. So again, I am not directly related to AKR, like I have never met him personally, neither I was a student of him. But the first memory that I have of AKR is when I was in class 9 in 2005 when he died. And at that time in Telegraph, there used to be in every Monday a know-how section. And there was an article on AKR named Solitary Pursuit. And I think that's a very apt title for an article, because as Professor Shayonkar already showed, for the first 10 or 15 years of his life, all the papers that he wrote was just a single author paper. So indeed a solitary pursuit. So what I'm going to talk today will be about black holes. So therefore AKR will definitely be a very important role, even though I will not directly mention to his work. But rather another Indian, C.V. Visheshwara, will actually play a key role in what I am going to discuss here. So this work I have done in collaboration with Mostafizur Rahman, who is a postdoc at IIT Gandhinagar and currently a JSPS fellow, and Shubhadeep Sarkar, who is a PhD student of Srijit Bhattacharya in IIT Allahabad. And again, I am from IACS, and you heard some grim story that AKR faced at IACS. So I mean, I don't know whether I should be ashamed of it at this stage, but yeah. But at the same time, of course, proud that at least he worked there. So this is a brief outline of my talk. I mean, just incidentally, I mean, today at 7:30 I got the mail that this paper is now accepted. So therefore I could not put it there right away. So I will discuss these few topics. I mean, it may sound foreign right now, but hopefully as I progress, this will settle down to something interesting. So first about hyperboloidal slicing. So what I'm going to talk about is about black hole perturbation theory, and I will discuss each of these in detail. Then the pseudo-spectrum for asymptotically flat black holes, and these results have appeared only in 2021 and so, like maybe 1 or 2 years old at max. And our interest is what happens for asymptotically de Sitter black holes, and implications for the stability of the quasi-normal modes and possible future directions. So first of all, before I start, just an idea about why we are so much interested in black holes. I mean, of course, not just because it is black and we cannot see, and anything can be said about it. So black holes can be constructed out of normal matter. So you can have a collapsing dust ball, and it collapses and forms a black hole. You know, the Oppenheimer-Snyder model is something you always start with. And you have a very simple scenario over there. Then black holes are unique and they have universal properties. So for example, if you use Einstein's equation, and if I say you have staticity and spherical symmetry, then you uniquely have the Schwarzschild solution at your disposal. Then black holes behave as thermodynamic objects with temperature and entropy, and this is something we have been knowing for years, starting from Bekenstein. And every day when you hear about talks on quantum gravity, in one way or other, people will harp on these results to argue that black holes are really the road to quantum gravity. So you should understand black holes better if we want to aim to get a quantum theory of gravity. But that is for the theory side. On the observational side as well, there are questions like, are black holes stable? Because if something is not stable, it's not worth giving so much attention to it. But they are indeed stable under all possible perturbation, at least black holes in general relativity. And just as I mentioned, I will be talking about general relativity alone. I mean, whether we talk about other theories of gravity, I mean, that also can be done, but that may be in a different talk. Now they are stable. If you have scalar perturbation, electromagnetic perturbation, or gravitational perturbation, you can show black holes as stable. I will describe how this is actually done. And we have really seen consistency with black holes. For example, we have the observation from the Event Horizon Telescope, which observed the shadow of the M87 star and the Sagittarius A star, and the results are consistent with that of a black hole. We have also observed gravitational waves from binary black hole coalescences using the LIGO and Virgo observatories, and they are also consistent with the prediction that it's a black hole. However, that's not the full story, but I mean, that again will not be the topic of today's talk. So now, I mean, I could have just some historical overview. I mean, I could have also said that everything started from John Wheeler. I mean, almost everything in our physics. But so you can see them in the black hole stability analysis was started by Reggie and Wheeler in 1957. But to be honest, the actual quasi-normal modes, which I will be the focus of my talk, was first coined by C.V. Visheshwara in 1970. So that's why I sort of titled it that the topic that I am going to discuss started in 1970. So the idea is that you perturb the black hole, like when you perturb any physical system, the system sort of have some normal modes, in this case quasi-normal modes, and then it settles down to another stable configuration. So to prove the black hole is stable, you have to show that with time the perturbations gradually decay out and it does not stay there forever. So for that you have your quasi-normal mode, but the normal mode frequencies, and for black holes there is a real part and the imaginary part. I will come back why it has real and imaginary part, and that will be a focus of this talk. And the sign of the imaginary part actually is such that you can show that with time the perturbations decay. And therefore, if you go to large enough time, then there are no perturbations or they become very small to be precise. And therefore, it signals that there is stability of the black hole, in the sense you are perturbing the black hole and the perturbations are decaying with time. So you are again getting back your good old black hole. And in general relativity in particular, black holes are definitely stable. And what you observe in the LIGO and Virgo are the lowest lying QNM. So just like the normal modes, there are various overtones. So there would be a lowest lying mode, and then there would be excited states which are present. So just like when you solve a quantum mechanical problem of a particle in a box, there would be a lowest lying level and there would be higher overtones which are present. And the lowest lying mode is the one which is the least damped, and therefore if you look at late enough times, it's the least damped mode which is going to contribute, and therefore that is what you actually see in your LIGO and Virgo. Now just to mention, I mean, currently there is a controversy going on which is about the higher overtones and non-linearities. So this would be clearer if I just show you this diagram just for pictorial purpose. So as you know, there are these three phases of your gravitational wave signal. There is a in-spiral phase when these two bodies are sort of coming closer to each other. There is a merger phase where they are merging, and then there is a ring down phase where the QNMs are, and that's the part we are interested in. So the most pertinent question here is where does the merger end and where does the ring down start? So that's a very ambiguous point of time. Various people take various stands. So some people say, I mean, after the merger, you go for 10 times the mass of the black hole in geometrized unit, and that's where the QNMs or the ring down should start, or the linear theory should be valid from that time instant. Some other people say you can actually start at the merger itself, but you need to take into account higher overtones. So therefore, there is even now the controversy that I am mentioning is whether you should talk about non-linearities in GR when you talk about the initial phase of the ring down, or whether you should model it just by adding higher and higher overtones is an open problem. So people are saying that overtones are not enough because this is like overfitting the problem. You have more number of parameters, so therefore you can fit it well. So non-linear effects must be taken into account, and that is a controversy which is going on. So if you are interested, I mean, I can share the references on that. However, the quasi-normal modes have also some very interesting feature. First of all, these modes are complex, which you normally do not see. And that is because the black hole is actually a dissipative system. So why? Now, when you get the quasi-normal modes, what you do, you solve a differential equation with boundary condition. So these boundary conditions are the waves or the modes should be perfectly ingoing at the black hole horizon, and it should be perfectly outgoing at infinity. So that means it's a system which leaks out radiation or leaks out whatever is inside the system, either through the horizon or through the infinity. So therefore, that is exactly what happens to a dissipative system, and this is the boundary condition that you put in. And as a consequence, even though the linear perturbation, I mean if you have known the Rege-Wheeler equation, the Zerili equation, all the linear perturbation equation, they are very much like the Schrödinger equation. We apply the WKB approximation and so on and so forth, but they are not really our standard quantum mechanical system. Because quantum mechanical systems, which we normally study in our undergraduate or graduate days, are conservative systems. So therefore, the energy eigenvalues, for example, are always real. They are never complex. But the black holes are dissipative, so that's why the eigenvalues, which are the quasi-normal modes, are indeed complex. So this means one of the most important theorem in quantum mechanics, which is the spectral theorem, which guarantees that if I perturb my operator, like the Schrödinger equation, I have a potential. Suppose I perturb the potential by a small amount. The eigenvalues are not going to change by a very large extent. The eigenvalues are also going to be perturbed by a small amount. And you know, the time independent perturbation theory precisely hinges on this particular fact. However, for the QNM, that is not true, because the spectral theorem only holds for self-adjoint operator or Hermitian operators, as you say. But for a dissipative system, you cannot describe it by a self-adjoint operator. So the operator that describes the evolution of perturbation in black hole spacetime is not really self-adjoint. And therefore, the spectral theorem no longer applies. So that means if you perturb the potential that field or the perturbation experience in a black hole background by a small amount, the quasi-normal modes can shift by a very large distance. So for example, it was at some location, you apply a very small perturbation, it will go to a very different location, which can in principle be possible. And these perturbations are ubiquitous. So just like I am perturbing all of you with this boring talk, so similarly black holes are always getting perturbed by matters surrounding that black hole, like there can be dark matter, there can be small planets, there can be other black holes which are perturbing the original black hole which is present. So therefore, perturbations are always there, and therefore there is no reason to expect that the quasi-normal modes that you compute for the isolated black holes are going to be there. And this problem, very interestingly, was first addressed again by Visheshwara in 1996. I mean, when people are just grasping the QNMs, I mean, at that time he was thinking about the stability of the QNMs themselves. And what he did, he sort of replaced the potential by some simpler potential, because at that time not much numerical techniques were available. So he used some simple models where things can be done analytically. And what he found are these two results, that is the fundamental quasi-normal modes are stable, but the overtones are unstable. Then afterwards, Nollert and Price in 1999 did a more extensive analysis, but with a somewhat weird perturbation, some step function like perturbation, some delta function like perturbation, and so on and so forth. And their answers, or what they found, are completely sort of opposite to what Visheshwara found. What they found are that all the QNMs are unstable. Whether you talk about fundamental QNM, whether you talk about overtones, it does not matter. All of them are unstable. So that means if you are looking at the behavior or the evolution of the perturbation at late times, it is actually governed by the perturbed QNMs and not the QNMs that your code will give you when you apply it to the Rege-Wheeler or the Zerili potential. So that means what you are actually seeing in LIGO and Virgo, are they really the fundamental quasi-normal modes which we are using to infer the mass and spin of the black hole, or are they really the perturbed quasi-normal modes, because there are many things in the environment of the black hole, and in that case you are really measuring the mass and spin wrongly, because these two are not directly correlated in that sense. So that is a possible dilemma, and the question is who is correct. So very fortunately for me, but maybe unfortunately for many, that this question was not answered till the late 2020. But before I go into that, I can tell you what you should expect. So what we are interested in, your boundary conditions are same, things are always ingoing at the horizon, things are always outgoing at infinity, but the potential is modified. I can ask the same question in a different way, that suppose the potential is same, but I change the boundary condition, what happens? Which is also a pertinent question to ask. In that case, people have shown that the quasi-normal modes are drastically modified. In particular, if you look at the late time signal, you would only expect the first part if you have black holes in GR. But if you have such weird boundary condition where something is prohibiting you from going inside the horizon, you have the repeated signals which are called echoes coming up into your time domain waveform. So that means QNMs are indeed susceptible to your boundary condition change, and if you change your boundary condition to something different, your quasi-normal modes can change very drastically. But it's not very clear whether change of boundary condition and change of potential would have same effect, so it is worth looking at what really happens when you change the potential. Okay. So for that, normally we work in the standard TR theta phi coordinate system, right? I will not go into rotation anyway because that is a difficult thing. So we'll just talk about static and spherically symmetric black holes, the most simplest case possible. Schwarzschild, for example, and for the case of asymptotic flat case, and for asymptotic de Sitter, Schwarzschild de Sitter. These are the only two examples I will take. So therefore, here what I plotted is the time coordinate, and here is the r coordinate. So you can see like the waves. So what are the boundary conditions? The boundary conditions is the waves are outgoing at infinity. Now that infinity is actually future null infinity, of course not space-like infinity. So therefore the waves are really following this u equal to constant lines. So these are the null surfaces which are present. On the other hand, the standard coordinate system that is used at t equal to constant, and these are space-like surfaces. So therefore, what you need, you can of course work with the null surfaces, but if you want to do not get around of your comfort of having a time or having a clock at your hand, you define a new time coordinate which is this tau, and this time coordinate behaves in such a way that it asymptotes to this null surface when you go to r tends to infinity. So this type of time coordinates are called the hyperboloidal coordinates, and these coordinates are absolutely essential when you do, not absolutely essential, but are very convenient when you do numerical analysis of the QNMs. For the most important reason that in this new coordinate system tau, you do not have to impose any boundary condition. I will explain why. The fact that modes should be outgoing at infinity and they should be ingoing at the horizon are automatically implied. So there is no boundary condition that needs to be imposed. I will choose some sigma, this tau and some other radial coordinate sigma in such a way that the boundary condition will come out of the differential equation without imposing any of that. So it would be a consequence. So as I said, this boundary condition will not be imposed by hand, but it becomes automatic in this case. So the first step in doing this is to go to a hyperboloidal foliation, which is determined by this tau. So let me go through it slowly. Don't get frightened with all these equations. It's pretty simple. So the general strategy is first you compactify the radial coordinate. Okay, you have a radial coordinate which goes from your horizon to infinity. Now we do not want infinity, so you want it to scale down to a small finite region, which can be done pretty easily. Then we want to transform to this new time coordinate tau, and we want to use the property that the horizon is a null surface, and using these three we can arrive at the hyperboloidal coordinate. So first is you have this static spherically symmetric metric with gtt equal to g upper rr with a minus sign, and this is your tortoise coordinate r star, which is dr over f, and this sigma is my compactified radial coordinate. So my r goes from rh to infinity, horizon to infinity, but my sigma goes from 1 to 0. I will show you in the next slide how that can be done. Now after you do that, you have this free function rho of sigma at your hand, which you have to choose in some way, and then you make the series of transformation t of t comma r. From that you go to the null coordinate v comma sigma, and then you go from v comma sigma to tau comma sigma. So tau and v are related through this h naught, which is called the height function, and this sigma, this f of r you can replace, this integral you can replace by g of sigma. So effectively you have one unknown function here, rho of sigma, and you have this f of r. When these two functions are given to you, you can determine everything else. For example, this h naught will satisfy this differential equation where beta is given in terms of rho, and this f is the function which is sitting on the metric. So only with these two choices you can determine what is the height function, you can determine what is your tau naught, and so on and so forth. But of course, this is a gauge, there are gauge freedoms which are left. I mean, the choice that I have taken is called the minimal gauge choice. I mean, you can choose some other coordinate system, in the sense like maybe you can add here some other functions of sigma which are regular and so on and so forth. But I mean, that is a gauge freedom which is always there. So I'll just show you what are the physical meaning of it. I mean, as Professor Shayonkar said, I mean, after I gave all this longish mathematical slide, maybe many of you are sleeping, so just to wake you up. So this is the physics what is happening. So you have the time coordinate on the y-axis, and x is like your tortoise coordinate, which runs from plus infinity to minus infinity. This is the tau coordinate, which is this hyperboloid on this t_r star plane. And this distance from the x to the tau constant is what is called the h of x, and that is the height function that I had defined. What you do, you take plus infinity to a finite location b, you take minus infinity to another finite location b, and this in this new coordinate tau comma x or sigma, it becomes a straight line, and your height function is also embedded into this coordinate choice. So this is how it can be done. So suppose I define my r by lambda. Lambda is some parameter. It can be 2m, it can be 3m, the mass of the characteristic length scale of the system. So this is related to sigma like this. So suppose you put sigma equal to 1, then you see that your r by lambda is given by sigma plus, right? So that is like your r is equal to r plus, which is your horizon. On the other hand, if you put sigma equal to 0, you can see that your r is infinite. This is a simple way to parameterize that relation between r and sigma, so that when r goes from r plus to infinity, or in the tortoise coordinate minus infinity to plus infinity, your sigma actually runs between 0 and 1, where 0 corresponds to your r equal to infinity and sigma equal to 1 corresponds to your r equal to r plus. And this h naught of sigma also turns out to be this, because you know what is your rho of sigma, which is this quantity on the top. So you can solve the differential equation and get your h naught of sigma. So to be honest, there are finite terms in sigma, but those terms, as I said, can be rid of by coordinate choices. So I have only kept the terms which are divergent at the two limits. This is divergent when sigma goes to divergent, when sigma goes to 0, and same over there. So these are the only two terms we have kept. There can be terms of order sigma square, and so on and so forth, which are not very relevant for our purpose. Now we want to do it in de Sitter. Of course, that was for the asymptotic flat case. So just to tell you what are the Penrose diagrams of de Sitter in various coordinate charts. So this is a Schwarzschild de Sitter. So you have a singularity which is r equal to 0, which is present. Then you have the event horizon, which is this h plus 45-degree line. And then you have the cosmological horizon, which is hc plus, because Schwarzschild de Sitter has two horizons, the event horizon and the cosmological horizon. And then you have this chi plus, which is present for de Sitter. These are the t constant foliation. So if you are looking at t equal to constant surfaces, this is how you foliate your spacetime. If you are looking at v equal to constant slices, which are null lines, so they have to be at 45 degree, then this is how you foliate. And finally, if you go to this hyperboloidal slicing, this is how the foliation works. And you can easily see they all start at the event horizon and they all ends at the cosmological horizon, because that's what you want. When you solve the quasi-normal modes in asymptotic de Sitter, what you do, you put ingoing boundary condition at the horizon, that is everything goes inside the event horizon, and you put outgoing boundary condition at the cosmological horizon, that is everything goes out of the cosmological horizon, and that is sort of neatly captured into this tau equal to constant coordinates. And these are the redefinitions again. So you can see if you put sigma equal to 1, you get sigma plus, which is r plus, and if you put sigma equal to 0, you get rc by r plus, and so effectively you get here r equal to rc. So again, r equal to r plus to r equal to rc, the two locations can be mapped back to 0, 1, as in the asymptotic flat case. And this is the h naught in this case, which has a log sigma behavior. So we have found out what are the corresponding hyperboloidal slicing for asymptotic de Sitter. Now let us look at the wave equation. So normally when we write down the wave equation for any perturbing field, this is the equation that we write down. Del 2 by del t star minus del 2 by del r star square is the standard box operator. Then you have a potential term V acting on your perturbing field phi equal to 0. But as I said, t and r star are not very good coordinate system to choose. And one question that you could have asked is that, look, quasi-normal modes are comes with e to the power I omega t, right? So these are like generators coming from del del t operator. It turns out that del del t is actually del del tau except for a rescaling. So that means the quasi-normal modes which you get in the t coordinate are going to be exactly the same in the tau coordinate except for some constant rescaling by mass, say, for example. And it sort of takes a pretty ugly form here, so which you may not want to look at, but I want you to look at this particular expression p, which is 1 over g prime, and as you can see, this p is the term which sits in the double derivative. So this p is multiplied with del sigma square acting on phi, right? And what was g? If I go back to the previous slide, you can see that g is nothing but r star, and that is defined as 1 over f. So that means at both the horizons where f of r vanishes, this g and this g prime will actually diverge, which you can easily check, and therefore what you have is that your p vanishes at the two locations of the horizon. So at sigma equal to 0 and sigma equal to 1, p of sigma vanishes. So as p of sigma vanishes, that means at the horizon these are not second order differential equations, these are first order differential equations, because the del sigma square term, the coefficient of that is actually 0. And when you solve a first order differential equation, you will actually get only one solution, I mean either e to the power plus I omega x or e to the minus I omega x. What you will get will be determined by the sign of the first derivative term. And that sign you can show will depend on this derivative of this p operator. It will have precisely the correct sign so that the solution is outgoing at infinity and solution is ingoing at horizon. So that means you do not have to impose the boundary condition. The boundary condition is already there by the choice of this particular coordinate system, and that's why it sort of helps when you do the numerical study. So yeah, so this is the case for de Sitter, and just to show you that at sigma equal to 0 and at sigma equal to 1, this p of sigma identically vanishes, which is also true for all the other cases like Schwarzschild, Reisner-Nordstrom. You pick your favorite, static, spherically symmetric, metric, it will be true in all of them. And the only difference is for asymptotically flat case, sigma equal to 0 has a double root, means sigma square, but here there is a single root, that's all. I mean, but it still goes to 0. And as I said, this is a characteristic property of the hyperboloidal foliation. Now let me not go through it, let me go directly to the next part of it, which is the failure of the spectral theorem. So what we do, so we have a non-self-adjoint operator A. So first of all, if you have a self-adjoint operator, your eigenvalues are real. I mean, that is something we always learn in quantum mechanics, and eigenstates are orthogonal and so on and so forth. But since here A is not a self-adjoint operator, because then of course the quasi-normal modes cannot be complex to start with, they has to be real. So therefore the eigenvalues are lambda and lambda star because they are complex. And the eigenfunctions also need not be same. Here the eigenfunction is V, there the eigenfunction is W. So you can ask what happens when A acts on V, it gives you some lambda times V. When A acts on, or A dagger on the left hand side acts on W, it gives you lambda star on W. And therefore from that you can ask what happens when you perturb this operator A, the eigenvalues are going to be perturbed as well by an amount epsilon. So the idea is you have an operator A, you are perturbing the operator by some A plus epsilon delta A, where epsilon is a small quantity, right? And the eigenvalues are going to change depending on your epsilon, and this difference should be smaller than epsilon times this kappa I. This is something you can prove, and this is what is called the spectral theorem, where this kappa are given by the magnitude or the norm of W times the norm of V divided by their inner product. Now let us suppose your A is actually a Hermitian operator or a self-adjoint operator. So in that case what happens is that your W and V, they are orthogonal to each other, and therefore so they are proportional to each other because A is same as A dagger, and therefore if you put W equal to V, your K will turn out to be 1, right? And that means your lambda I epsilon minus lambda is less than epsilon. So that means if you perturb the operator by an amount say 10 to the minus 10, your eigenvalues are going to change by an amount which is less than 10 to the minus 10. So that means the spectrum is stable. However, when the operator is not self-adjoint, then there is no reason for W and V to be same because A is not equal to A dagger, and in particular it can happen that W and V are actually orthogonal to each other, and in which case this inner product is going to be as close to 0 as possible in general. I mean, maybe in some specific cases it does not happen, and your kappa can be pretty large. So that means your difference in eigenvalue can be very large compared to whatever perturbation you have given to the system, and that is what which demonstrates that the spectrum is actually unstable. And that is precisely what happens for the case of black holes. So this is again sort of a restatement of that. So the eigenvalues of the non-self-adjoint operator A, they are spread out all over the complex plane just like the QNMs, and you take a perturbation A going to A plus epsilon into delta A, and if the eigenspectrum drifts away by an amount more than epsilon, then that is what it means by spectral instability, and that is what we want to do. So we have the black hole with a potential with that V, Rege-Wheeler, Zerilli, whatever your favorite potential you pick, and then you change that potential. I mean, you can change it by various amount. People can change it by a Gaussian profile, you can change it by adding some cosine function with some parameters. The point is, when you tune the perturbation, as you increase your value of epsilon, you ask what happens to the quasi-normal modes, how do they drift away, do they remain close to their original location or they do not. I mean, normally we do not expect them to be close to their original position because it's a non-self-adjoint operator, so spectral theorem does not apply. But unless you do the computation, you cannot just see that. So I will again sort of skip these things, and I will just go back to the pictures because that's what you can appreciate more. So first you start with the Poschel-Taylor potential. So these are taken from this paper by Jaramillo which I was mentioning in 2021. So Poschel-Taylor is the most simplest potential where you can solve everything analytically. So let me explain what is being done here. So this is the imaginary part of the quasi-normal modes, and this is the real part of the quasi-normal mode. You can see these red dots over there, right? So the red dots are the unperturbed quasi-normal modes. So that means you do not add any perturbation, you simply solve your equation with the Poschel-Taylor potential, and these are the places where the eigenvalues would be located. Now what you do, you perturb the potential and see how the QNMs are going to migrate away. So those lines are given by these white contours which you can see. Now contours of course should correspond to some strength of the perturbation, so that strength is in the color coding. So what it means is that if you perturb the system by a perturbation of a strength 10 to the minus 25, then these are not going to be perturbed because you can see these are not in the green region. So but the modes over there, they are going to be perturbed because that corresponds to this particular color code. If you perturb it by a strength of order 10 to the minus 5, then even these modes are going to be destabilized. And their conclusion is, I will show you a more detailed plot in a minute, is that the fundamental mode they found to be not going to be destabilized. However strong perturbation you add, they added perturbation up to 10 to the minus 1, but even then the fundamental modes were exactly at their same location. So the main conclusion of the asymptotic flat story is that what Visheshwara said is actually the correct thing to do. The fundamental modes are not unstable, but the overtones are. So they sort of ruled out what Nollert and Price said and reinforced what the result that Visheshwara had obtained in 3 years before. Now you may ask what happens if it is non-self-adjoint. So you can, for Poschel-Taylor, you can remove the non-self-adjoint part, and then the operator becomes self-adjoint. For that case, this is how the QNMs look like. The imaginary parts are all 0 because it's a self-adjoint operator, so QNMs have to be real, so there is no imaginary part. And if you just sort of zoom it in, you can see the pseudo-spectrum contours which earlier were divergent are now only concentric circles. And that is what you expect, because your lambda I epsilon minus lambda I is less than epsilon. So these are all equations for circle. So that is what you expect for a stable spectral problem, and that arises when you have a self-adjoint operator without a non-self-adjoint term. Yeah, so here what they took is that there is a Poisson-Taylor potential, and on top of that they add a Gaussian perturbation. And they sort of checked it by putting that Gaussian at various places and seeing whether it indeed changes the value. So this is what happens when you add perturbation. So let us start here. So that there is no perturbation, it is 0. So these are the QNMs which are present. Then you add a perturbation of order 10 to the minus 16. So you can see the lower QNMs are exactly standing on top of each other, but after some point they are migrating away. And they are not migrating away in a closed region, they are migrating much far away from the original location of the QNM. You increase the perturbation to 10 to the minus 8. You can see even more overtones are destabilized. And finally, you go to a perturbation of order 1. You should not call it perturbation, but just for the sake of it. You can see that the lowest lying mode is still there. So whatever was your red dot, your black crosses are exactly on top of it, but the higher overtones are completely destabilized. So this was for Poisson-Taylor. Now you go for the Schwarzschild. So for Schwarzschild there is one problem. The problem is, you can see there is a red dots are all over this imaginary axis. So this is happening because in Schwarzschild the fall off is not very good. So that's why along with quasi-normal mode you also have late time tails which are due to the branch cut. And this branch cut creates a problem, because when you run this code, what happens is that they also picks up these branch cut points and things do not converge over there. So that is why you get all these spurious points along this imaginary axis. So you should actually discard them. And these other red dots which you can see are closely separated, they correspond to your Schwarzschild quasi-normal modes. And again you can see that they sort of go away from their original location when you add perturbation. Like if you add perturbation of strength 10 to the minus 30, these modes are going to be destabilized. If you add 10 to the minus 10, these modes are going to be destabilized, and so on and so forth. The lower one is just a zoomed version of it, because if this looks too crowded, this is how the separation looks, just the lower part of it. Now comes the instabilities. So what you do, you have the central line I am not interested in. As I said, it's a branch cut, numerical artifacts, and so on and so forth. The red dots are the unperturbed QNMs. And then you put a perturbation of order 10 to the minus 8. So this is a slightly different perturbation, not Gaussian, but like a cosine perturbation with two parameters, a strength and cos kx, say for example. So this k parameter is taken to be 1. That means the perturbation is over a very long length scale. You can see that they sit on top of each other. So that means your stability is there, at least up to this order of perturbation. Then you give a perturbation of order 10 to the minus 8. And you can see, except for the lower three modes, on which case the green and the red are exactly on top of each other, the overtones sort of move away. And they move away exactly, yeah, sure. And they move away exactly like the contours would predict. And if you sort of, increase the strength of your perturbation even to 10 to the minus 4, you can see that the lowest lying QNMs, they are still there. Whether you perturb or not perturb, but all the higher overtones are destabilized. So this sort of proves that at least for Schwarzschild, the fundamental mode is stable. The other thing that happens is that another very interesting thing is isospectrality, which is that the axial and the polar QNMs exactly sit on top of each other for Schwarzschild. That is broken now. So if you just plot here, the axials are the red and the polars are the blue, you can easily see that for the overtones, the red and blues are pretty separated from each other. So that means the polar QNMs and the axial QNMs are no longer same. So isospectrality is broken. And this is sort of summarizing everything. So you can easily see that the QNMs are drifting exactly along these white lines which the pseudo-spectrum predicts, and that depends on your strength. Like if you have 10 to the minus 8 or if you have 10 to the minus 4 with K20, the drifting is always along these lines. And the fundamental mode which are here, everything gets superposed. So therefore the fundamental mode is indeed stable. Now if you do the same analysis for Schwarzschild de Sitter, your life is simpler in some sense, because in asymptotic de Sitter there are no branch cuts, there are no late time tails which is present, because at late time also the fall off is exponential, not power law. But you get another set of modes. So there are two sets of modes. So these modes which are separated have a real and imaginary part. These are the photon sphere modes, because they predominantly come from the perturbation of the photon sphere. While there are modes along the imaginary axis which are not as dense as earlier, these are called the de Sitter modes. I mean, they sort of comes only because there is a cosmological constant. And this is for the case of scalar, and this is for the case of gravitational. And here also you can see exactly the same type of spreading when you add perturbations. Now let us ask what happens when you perturb the scalar mode. Let us go case by case. First is epsilon is 10 to the minus 10. So you can see all the modes, the reds are the unperturbed and the boxes are the perturbed. They completely overlap on each other, as we see for Schwarzschild. Then you go below, you make epsilon 10 to the minus 6. So in that case you can see that the higher overtones are going to destabilize, because the locations are going to be different. Finally, when you go to 10 to the minus 1, the fundamental mode is still more or less within the accuracy, but at the same time when you increase your value of k from 1 to 60, you can see even the fundamental mode got destabilized. I mean, it's small. But the argument is here also, I mean, the perturbation is of the order of 10 to the minus 1. The separation that we obtained is also of the order of 10 to the minus 1. So this is not really destabilizing the fundamental mode. It's not larger compared to 10 to the minus 1, at least when the scalar case goes. But on the gravity, the situation sort of changes. In particular, you can see from this plot, like this particular mode over here, it is highly destabilized. On the other hand, these modes are still pretty much in the vicinity. So we sort of concluded from here that the gravitational QNMs are more prone to instability than the scalar, and this is most easily seen with the variation with lambda, and this is something which is pretty puzzling. So what you would expect? You would expect as lambda becomes smaller and smaller, the fundamental mode would become less and less unstable, right? Because we had the Schwarzschild result, but we obtained the result which is quite contrary to that. So for example, here lambda was 0.1, then we change it to 0.01 and 0.001. This is for the scalar and this is for the gravity. For the scalar, the destabilization, as I said, is not that much. But for gravity, you can easily see that the destabilization increases as you lower the lambda. For lambda equal to 0.1, these two modes were almost coincident. If you decrease lambda, there is a difference, but the difference is enhanced when you make it smaller and smaller. So the reason being, as you lower the lambda, your de Sitter mode starts to dominate over your photon sphere mode, and this de Sitter mode have no analog in Schwarzschild, because Schwarzschild has no de Sitter mode. So that is why this lambda tending to 0 limit, at least what our results suggest, seems to be some sort of a singular limit. That is, you do not reproduce your Schwarzschild black hole result when lambda becomes small. And in particular, when lambda becomes even smaller, the stabilization or the destabilization is even worse compared to that. So I will, these are again the same sort of spectra. So you can see the destabilization exactly follows the pseudo-spectrum contours which I had drawn for various cases of perturbation. So this sort of shows how this pseudo-spectrum contours are useful. This is for scalar, this is for the case of gravity. You see exactly the same setting in all of that. So I will just end with a last bit of comment, what is relation to the strong cosmic censorship conjecture. I will just take 2-3 more minutes. Okay. So the point is, we have, Kerr black hole, for example, which is the most prominent astrophysical black holes, or a simplified version would be Kerr-Neumann, or sorry, Reisner-Nostrom. So in all of these cases, we have a Cauchy horizon, right? There is an event horizon, and inside the event horizon, there is a Cauchy horizon. And Cauchy horizon is always problematic, because if you pass through this Cauchy horizon, your future becomes unpredictable, and that's not a good thing to have. So people have I've argued, and actually they have also postulated, mostly by Christodoulou and others, that you should not be able to cross the Cauchy horizon with some regular, metric, some regular scalar field, and so on and so forth. Now, even though that seems to be true in asymptotic flat case, in 2018 people have shown that if you talk about asymptotic de Sitter black hole, that is not true. You can actually cross the Cauchy horizon with sufficient regularity, and therefore your strong cosmic censorship conjecture, as it is called, is going to be failed. So it was resurrected, it was satisfied later on by Wald in end of 2019, where he used the semi-classical Einstein's equation and said you need quantum fields in order to save from this strong cosmic censorship. But now, since we found that, and this actually comes from this parameter beta, which I have written here, and so this parameter is dependent on the lowest lying quasi-normal modes imaginary thing. So what happens is that Cauchy horizon has an infinite blue shift, so energy density grows exponentially, but the perturbations decay exponentially, because as I said, for asymptotic flat case it is a power law, so the exponential behavior always wins. But for asymptotic de Sitter, it's a power law, exponential decay. So there is an exponential growth competing with an exponential decay, and it may be possible that the decay wins and you can go through the Cauchy horizon without much of an issue. So this beta depends on the imaginary part of the lowest lying QNM. And what I have just shown you just a few slides before is that the imaginary part of the lowest lying QNM is actually small when you add perturbations. So that means the beta is going to be small if you have a perturbation present. So using that and using these results, we could actually show, like earlier it was crossing this value 0.5, and that sort of tells you where the violation happens, but now it never sort of crosses 0.5. Because of the instability of the fundamental mode, the value gets reduced. And that means maybe we really do not need all those quantum fields to address the cosmic censorship puzzle. Maybe it is just that the perturbation and instability of the QNM is what is responsible and is going to save the cosmic censorship conjecture by rendering extension across the Cauchy horizon impossible. So with this I just conclude. So just to argue, like the hyperboloidal coordinate system for de Sitter, that is something we have done, and they are useful for doing numerical relativity in de Sitter, maybe if someone is interested. Now we have determined the pseudo-spectrum of both Schwarzschild de Sitter and Reisner-Nostrom de Sitter. I did not show Reisner-Nostrom de Sitter because structurally it is same, it's just more complex. And then we could argue about the fact that the lowest lying QNMs are actually unstable for asymptotically de Sitter black hole, though they are stable for asymptotically flat case, and it has consequences for the strong cosmic censorship conjecture. So we are currently working on a few extensions, like for example what happens in the case of a BTZ black hole, or what happens in the context of anti-de Sitter. So there have been 2 papers just last month where they tried to understand the same for anti-de Sitter, and their conclusion also more or less the same, like the QNM of anti-de Sitter black holes can also be destabilized in light of what we found for de Sitter. But these are all directions in progress, so maybe we will have better understanding of this in future, and maybe we can discuss that in our next meeting. So thank you all for your patience and attention.
Thank you for such a nice talk.
Who is speaking?
Here.
Oh, yeah.
Okay. I have a question. If we perturb the tangential stresses in the OSD general model with the tangential stresses, OSD gave the ideal assumption like homogeneity and zero pressures are considered.
You mean cosmological context?
No,
or-
in the dynamical gravitational collapse.
Okay, okay.
Now, if
yes.
we perturb this tangential stresses of p theta and p phi of Einstein equation, then you know the final state of the initial gravitational collapse data will be different from
Yes.
the black hole. But you state the black holes are stable under all possible perturbations.
Yeah, but I did not mention about any formation channel, right? I mean, that's an initial value problem. What I said, you already have a black hole formed somehow, okay?
Okay.
Maybe God has given it to you if he exists, he or she exists. And then you are perturbing the black hole by, throwing in some matter or maybe throwing your colleague who is
So
perturbing
already
you.
form black hole.
Yeah, yeah,
Okay,
sure.
fine.
And then you are asking whether it again comes back to a similar configuration.
Okay. So, and the second, I have some confusion regarding the stability.
Okay.
Your title suggests the stability or instability of quasi-normal modes.
Yes.
But what I understood, the quasi-normal modes is the frequency decaying with time.
Correct.
But is it related to the stability of space-time metric or a quasi-normal
Sure.
mode?
So the point is quasi-normal modes denote whether your space-time metric is stable. In the sense like your quasi-normal modes has an imaginary part and
Yes.
that tells you that perturbation should decay with time.
But the
But what I am asking here is not about stability of space-time but about stability of the quasi-normal modes themselves.
Okay.
So if I just show you this plot, maybe where was it? Just give me a moment. Yeah. So you can see that even though, or maybe the one before. So you can see even though this mode is sort of reduced by some amount,
Yeah.
but the imaginary value is positive. So what it means, the QNMs are unstable because they are not at their original location if you perturb them, but still they decay.
Okay.
So therefore the space time is stable. There is no doubt about that, but the location of the QNMs are unstable.
So is it, we can say the existence of quasi-normal modes conclude the stability of
Existence
space-time?
of quasi-normal modes with positive imaginary part, I mean depending on your convention,
Oh.
that tells you it is stable.
Fine. One more question last.
Yes.
You said about the Cauchy horizon.
Yes.
So how is it predictable? If you cross the Cauchy horizon in this anti-de Sitter space-time,
Yes.
then is it predictable? In fact, I know the Minkowski, FLRW, and Schwarzschild are
It
predictable.
is never predictable. If you cross the Cauchy horizon, you cannot
Yes.
predict anything. I mean, you can predict something, but not all of it. But the point is, I mean, you cannot cross the Cauchy horizon.
Right.
So it's like saying you have some problem, you just cut it at the beginning. So the argument of Christodoulou is that the Cauchy horizon should turn into some singular region,
Yeah.
so you should not be able to even cross it. But what it shows is that if you are in de Sitter background, then you can actually cross it in some sense. And classically, of course, if you only have classical matter. What we are arguing is that that is only true for unperturbed black holes, in the sense where there are no environmental effects.
Right.
But since we always expect environmental effects to be present, a black hole is never really isolated. So this environmental effect should change the QNM spectrum and thereby make, the Cauchy horizon again singular, something like that.
Thank
Just
you.
that, okay. Maybe we can take this and then go back to you. Yeah. Yeah, please.
Two questions. One is operationally from the signal, how many modes can you distinguish?
Right now only the fundamental mode, and there are some claim that they have seen the first overtone. You cannot distinguish anything more than that.
So from the signal itself, I cannot isolate any
No.
frequencies.
But what you can do is that, suppose you assume that it's a Kerr black hole, then if you know the fundamental mode, you know the mass and spin,
Correct.
and then you can predict what are going to be overtone. So by substituting that, you can get a model signal and you can feed that to your data. And you will see that it fits very well. I mean, that's all that.
So now second question is related to, if I had a perturbed spectrum,
Yes.
I use its fundamental mode, the lowest frequency.
Yes.
I pretend that to be the unperturbed one and get some mass. So how is the relation between the frequencies change under perturbations?
So for asymptotic flat case, the
Others take
perturbed,
asymptotic flat, yeah.
for perturbed and unperturbed QNMs are same. The fundamental QNMs, they do not change. That is the main
No,
result.
fundamental and next one, let's say.
Next one is going to change,
Yeah.
but that will depend on how much the potential is perturbed. So, for example, one nice calculation one can actually do, I mean, I have suggested some of my students, is that suppose you have a black hole in a galactic environment, then you can try to find out how much the metric is going to be perturbed. And that is going to affect this QNM. So, you can actually calculate what is this strength of this epsilon parameter. And using this analysis, you can find out how the first overtone is going to migrate away. So then one can do the analysis that you are suggesting.
So
you can
which means you can get two information, not only the
Yes.
Information about the black hole, but also about the perturbation.
Exactly, also about the environment. That is actually the goal. I mean, if at some stage you could find these perturbed QNMs, you can tell about the environment.
So that is assuming that the fundamental doesn't change.
Yes.
If it changes, then
Yeah,
we
but
don't
that people are more or less sure that fundamental mode for asymptotic flat black hole is not going to change. I mean, whatever. Yeah, that is stable. Thank you. Yes, I think. Okay, I will take yours. Yeah, please.
So let's say black hole is formed somehow. Then if we throw some charge, then also it will not be stable, right? It will convert to naked singularity.
That
if it
is
acquires
not
charge from somewhere.
I'm not quite certain, because there are paper by Wald which actually showed that up to second order you can show that you cannot overcharge a black hole. That's what you were mentioning. So I mean, changing a black hole to naked singularity is not a very good business, I would say, and there are ways you can avoid that. So that is the other cosmic censorship that you are saying, the weak version, and I don't think that is possible.
Okay, and
Because there would be back reaction and other things, so
Okay.
it may not be.
okay, and this tau is equals to constant foliation will
Yes.
work for globally hyperbolic spacetimes only, or other
No,
non-globally
I mean like
hyperbolic?
Rice-Nostrom, which is not globally hyperbolic, even then you can use it.
Yeah, okay.
Because you are just connecting, the horizon to infinity. You are not going beyond the horizon,
Okay.
right? So the region you are interested in is globally hyperbolic, so it should work.
Okay. Thank you.
Yes.
Oh, I just had a short question.
Yes.
So this instability, how does it depend on L, the angular moment?
Not much. I mean, if you change your L, I mean, so that will change, of course, but there is no coherent way of saying whether it is going to be larger or smaller. So, but it does change, but it's not a very drastic effect,
Okay.
I would say.
And do we have an understanding of this breaking of isospectrality? That why is it happening? Like
It's just because, I mean, the isospectrality comes because there are some properties, or you can relate the Regge-Wheeler potential to the Zerilli.
Zerilli.
But with this perturbation, that transformation does not work.
Okay. Okay.
So therefore, these two, the Regge-Wheeler wave function and Zerilli wave function, which you can relate one to other, is not present with perturbation. So therefore, isospectrality
Okay.
should be broken.
Thank you.
Yes.
I have a very naive question.
Please.
You said that there is infinite blue shift at the Cauchy horizon.
Mhm.
Can you explain that a bit?
Okay, so generally when you go to the black hole event horizon, you have an infinite redshift, right? I mean, people say like if you throw, I mean, a star is collapsing, it will take an infinite time to cross the event horizon, correct? That's because there is an infinite redshift. So light will take infinite time, the frequencies will become redder and so on and so forth. Just the opposite happens at the Cauchy horizon. I mean, that's the best way to think about it. So just like for the case of event horizon, there is an infinite redshift, which happens exactly due to an exponential decay in some way. That changes to an exponential growth and hence blue shift. Right? I mean, red means it is going to be dimmer, right? Smaller frequency. And blue means it is going to higher and higher frequencies. Yes.
Very nice talk, Shumanta. I just wanted to have sort of a clarificatory question. You see, if you take a particle in a box in ordinary quantum mechanics, infinite then you know that the momentum is actually not self-adjoint.
Yes.
If you have vanishing boundary conditions. But then there's this method, I think by Wigner or somebody, called a self-adjoint extension.
Yes. Yes.
Where you go from the vanishing boundary condition to the periodic
Correct.
or twisted
Correct.
periodic
Correct.
boundary condition, and then everything works
Yes.
out. I was just wondering whether your method has anything to do, is it like a version of the self-adjoint extension?
Yes, so this actually we had also wondered quite a bit, in the sense like this is as of now non-self-adjoint, can we have a self-adjoint extension? But the problem is the boundary conditions are by definition dissipative. I mean, things has to go away. So I mean, we do not know of any way of doing a self-adjoint extension of this. So I mean, but yeah, I mean, because of the boundary condition precise. Yeah, exactly. Because I mean, in the particle in a box, it was trapped in some finite region, but here by definition, it's a leaky system. So dissipation has to be there.
So thank you. There's another question.
Order in the sense like. Oh, okay. Yeah, this is a linear analysis. So what you can ask is that since there is a, things are becoming unstable, maybe if you do a second order calculation whether it is becoming important. Maybe not in this context, but in another context it becomes important. So I talked about this modified boundary condition. So there what happens, the QNMs have a very small imaginary part. So the pseudo-spectrum contours which I drawn, which are like this, at that time they will cross the real axis. And then what can happen when you do second order perturbation, the first order perturbation will act as a source for the second order perturbation, and there can be resonances. And this resonance can actually drive the system unstable. Not for black hole, but for the exotic compact objects. So for black hole, I don't think the instability would be there because.
The result on the fundamental.
Yes.
Is it all order?
No, it's not all order. I mean, at least first order, and people hopes that it holds for higher order. No, not all order.
So I think we should thank Sumanto for the nice talk. I'm sure given some more time, there would be more questions, but let us postpone that for the lunch time. So thank you, Sumanto. Thank you very much.
Thank you.